All right, in order to go through our log lesson today, we are going to recall on how to convert from a exponential to a log. So we said if we had an exponential, such as this one here, b to the x is equal to n. In order to convert this to a log, we drop the base. So we get log with a base of b, and then the n becomes the argument, and the x, which is my exponent, is free to become the answer. And that does go both ways. So the log base, the base on the log here is the base on the exponential. Our exponent becomes our answer here, and our answer becomes our argument. So the argument is always going to be the answer on an exponential. That's important for what we are going to do today. We're going to go deeper into learning what these logs are. All right, so we're going to talk about what each one of these logs represent. And we said the argument of the log, this argument here, would be the answer in an exponential. So we want to think through that on a number line like this, and then we'll think through all the logs that would match it. In order for it to be 0 here, that would have to be the exponent of 0. So we want to think about what exponent of 0 would give us that. So log base 2 of 1 would be equal to 0, because 2 to the 0 power is 1. So that's what our answer here would be. Log base 3 of 1 would be 0. Log base 4 of 1 would be 0. So any log with a base and then 1 as the argument is going to give me a value of 0, because anything to the 0 power is 1. So you want to think about that backwards. All right, if we think about this second one here, if we converted that to an exponential, that would be 2 to the x equals 1/2. Well, -1 would be that x value there, because that's what makes it do the reciprocal. So -1 goes here. So 2 to the -1 power would be 1/2. 2 to the first power would be 2. So this would be a log base 2 of 2. 2 to the second power would be 4. 2 to the third power would be 8. 2 to the fourth power would be 16. And then if we go back here, log base 2, 2 to the -2 power would be 1/4. So we filled out the number line. So this right here is -2. This is -1, 0, 1, 2, 3, and 4. In order to do the 3, you would do exactly the same thing. So log base 3, 3 to the first power would be 3. 3 to the second power would be 9. 3 to the third power would be 27. 3 to the fourth power would be 81. And if we go backwards, remember that negative exponent makes you do the reciprocal. So 3 to the -1 would be 1/3. And 3 to the -2 would be 1/9. All right, so the reason why we've done this is so that you can see where these logs are coming from and what value they have. This also allows us to estimate ones that we don't know. Here we see that these are just all the bases of 3. 3 to the 0 power, 3 to the first power, 3 to the second power, 3 to the third, and 3 to the fourth. But what happens when you don't have one that is a perfect number like that? So that's what we're going to talk about when we estimate them now. And we'll look at one of the ones on the bottom here. So log base 2 of 10. Log base 2 of 10. If I think about log base 2 of 10, well, here is 1, 2, 4, 8, and 16. So 10 would fall in between these two right here. Log base 2 of 10 would be right about here. Now, I know log base 2 of 8 is 3, and I know log base 2 of 16 is 4. And so I know that it has to be between 3 and 4. Since it's closer to the 3, I can estimate this is approximately 3.2. So knowing these logs, knowing where they come from, allows you to do the estimate without the calculator, and it also allows you to see, get deeper into what a log is. It is just an exponential, just showing that value. The next thing we're going to do is start our solving, because that's what we're going to do in this module 7 is solving exponentials and logs. The first one you've already done. You can solve with the calculator by entering one side of the equation into y1, the other side into y2, setting the window so that you see the intersection. That's what you want to do, is see the intersection. And then hitting second trace intersect and then the enter, enter. So that means we're going to take one side and put y1, the other side put y2 in order to see this intersection. You could also do that with Desmos. And so, for example, here I would do 4 to the x plus 1 and 8 to the 2x plus 3. I hit graph. There's my first one. There comes my second one. Now my window is way big here, so I could make this smaller. I'm going to go ahead and hit zoom 6, which takes us to the standard window. Doesn't really matter how big the window is though, since what we're looking for is the intersection and you just have to be able to see that. So we see the intersection happen somewhere right about there. So we're going to hit second trace intersect, enter, 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 and there it is at negative 1.75. So that is our intersection point. That would be the answer here. Now it doesn't take much math to do that, so it's kind of a little cheat, but that does allow you to solve using the calculator. You're just finding that intersection. With Desmos, you would just graph it, same thing, y1, y2, and then you click on it and it will give you the intersection point. Now to do real math, we're going to solve using common base. And we'll start with this first one. That's really easy. We have 5 to the x equals 5 to the third. Now when we have the same base on opposite sides of the equal sign there, we know that the only way that these are going to be the same value is if this exponent is the same as this one. That's the only thing that can happen there for both sides of the equal sign to be the same value. So x would have to be equal to 3. For the second example we see here, it says 10 to the 1 minus x equals 10 to the 4th. Just like we did on this one, we knew that this side had to be 3 because that's the only way they would give you the same exact value. Well, that's going to be true here. This 1 minus x has to be equal to 4 since they both have the same base. So all we have to do is take this 1 minus x and set it equal to 4. I then can solve like normal, so I subtract the 1. I get negative x is equal to, so now we've got negative x is equal to 3, and so x is equal to negative 3. You can always check your work by plugging that in there, and so we get 10 to the 1 minus negative 3, which turns that into a plus 3, is equal to 10 to the 4th, and that is 10 to the 4th equals 10 to the 4th, which is obviously the same. Now, all of them aren't going to be quite that easy, so we will talk about some that are a little bit harder. When they don't already have the same base, then you're going to have to work to get that same base. You're always going to want to think about the bases as 2, 3, or 4. They don't go much higher than that. So we got to think about what base can both 9 and 27 have. So both of those have to have a base to a power that would be equal to each other. So if we think about 3 squared is 9, and 3 to the third power is equal to 27. So that would be 2 that can have the same base and have the same value as 9 and 27. So 3 to the second power is the same thing as 9, and 3 to the third power is the same thing as 27. Now we have the same bases. You remember your exponent rules. When you have a power to a power like this, you multiply. So this would be 3 to the 4x is equal to 3, and this would be 3 times x minus 1. So we do have to distribute that all the way through. That's why I wrote it out twice there. So we get 3 to the 3x minus 3. Now we can do the same thing we did on the other side there. Since we have the same exact base on both sides of the equal sign, we can take this 4x and set it equal to the 3x minus 3. So 4x equals 3x minus 3. I subtract the 3x, and we get x is equal to negative 3. All right, we'll try another one here. We need to get the same base between 81 and 1/3. This one's a little bit harder to think through, but we can do it. We know 3 to the 3rd was 27 over here. Well, 3 to the 4th is 81. And so then to get 3 to have the same base here, we need this to have a base of 3. Well, we know when we have a negative exponent, it does the reciprocal. So we're going to have a negative 1 here. That's what gives me 1/3. So I can set this one up as 3 to the 4th. And I can set this one up to 3 to the negative 1. That part gets tricky. You have to have that number sense. And as you practice, you'll get better at those to make sure that you get those same bases. Once you have the same bases, that's the easier part. Power to a power tells us to multiply. Remember, we do have to distribute that all the way through. So that'd be 12 minus 4x. And again, here we distribute and we get negative 5x plus 6. Once they have the same exact base, then we're taking this and setting it equal to this one. So that gives us 12 minus 4x is equal to negative 5x plus 6. We're going to get our terms together, so I'm going to go ahead and add the 5x to get it to the other side. That gives us 12 plus x is equal to 6. I subtract the 12. X is equal to negative 6. All right, we're going to try one where you're going to see a little bit harder here. Again, we want to get the same base. And so we have two different options here. We can take this all the way down to a base of 5, or both of them have a base of 25 that they can be. This is already 25, and this one I can do 25 to the negative 1 power. So we get 25 to the 10x plus 8. I don't change it since it's already got that base. And then this one would be 25 to the negative 1 power. Now that they have the same base, 10x plus 8 would be equal to negative 4 plus 2x. I want to get my bases to my variables together, so I'm going to subtract the 2x. Now I'm going to subtract this 8 to get it to the other side and divide by 8. So x is equal to negative 3/2. So that's solving with a common base.